for building up all these kind of systems, we have the operating system, compilers, and then different sort of frameworks, right, for parallel processing. And then for debugging and diagnostics, we have a separate set of softwares. So all these systems come together one individual supercomputers. This may be a traditional way of putting every of the systems, every of the putting different kinds of hardware systems onto aggregated together in one place as a single entity. Or it might so happen that these are actually part of a grid system whereby we have a different kind of individual subsystems and each one of them connected and executed, right, in a distributed processing. Or nowadays, I think after the advent of the cloud computing, yeah, once again it's a different volume together. Next slide, please. When we are speaking about any deployment units, is either as a part of the industrial systems or as a part of the supercomputers, we generally tend to have a LRUs, which are nothing but line replaceable units, where each one of the system which you see is nothing but just like a what do you call plug in and plug, right? Each one of them part would be able to put them pull out and pull them back, right? Uh, this yeah. Now this is a traditional motherboard what we see on, whereby we see a motherboard with two CPUs, and then onto the right what you see as a white is nothing but a PCI extension, whereby we can put uh, GPUs, TPUs, or any other processing that would come on. Onto the left, what you see is nothing but a pluggable RAM slots, right? And then we have the interconnection slots and so on and so forth, right? This is a traditional motherboard, and that's what is also there. Yeah. Next slide, please. Okay, now getting into the more niche subject. So this more in terms of the architecture. Okay, what do we see? At the top level, we see only the application program, right? Now, uh, in terms of the HVC, once what we are seeing is not able to leverage huge amount of or deploying a certain kind of, let's say, weather modeling, right? We see an application which should be able to leverage a huge amount of computation down the layers. So it, which essentially is the one in the down, we can see that is the one which actually in the further level to the operating system, right? Whereby the operating system in lines with the hardware that is available, right? In terms of different kinds of instruction sets and the macro architectures, which is a combination of both the hardware and also the assemblers, which is supporting to it, which would actually run on the different execution units. Each of the execution is more analogous to a core execution on a single core, whether how much, whether it's able to, yeah. Next one, please. So what we see in this is nothing but we see application which is being deployed with supporting multi-core and multiprocessor. Now this supported by the hardware can have an instruction set supporting with SIMD or MIMD. Now as to the instruction set architecture, which is further executed at the execution level, we can see pipelining of instructions happening at the execution units. Okay, now, yeah, before we go further, anybody has any uh, any questions or anything, drop me a message if there is anything, right? actually look into it. Now, what okay, now as we go for what we see is nothing but the instruction set is based on the in the architectures we can see SIMD and MIMD, which essentially meant SIMD is meant for the single instruction and multiple data, and MIMD is nothing but multiple instructions and multiple data. So what exactly does it mean? And how is this able to leverage the computational capability of whatever that we are speaking on, right? And then we are speaking of high power computing, and then which essentially meant that ability to execute on the same system or on the different systems or on the wide varieties of distributed systems across the different areas, right? Now, this more or less in one sense translates to these instructions for acceleration, right? Which essentially meant that if I'm looking at a one single execution unit, I'm asking the system to execute once with a one single instruction, and then ability to execute multiple data to compute multiple data at the same time, right? This is SIMD. And then when I'm speaking of MIMD, I'm actually saying that there are multiple instructions that are possible and multiple data to be addressed for each of the operations in parallel. Now, I think if anybody has a uh, anyone has a understanding of they have done some let's say before 2010s, if anybody has done any C++ programming, or let's say up to 2011 or 2013 or earlier before, right? They would see that the execution is always in sequential, right? But if you look at the standards which have come post 2011, most probably with of course the compilers ingested probably at 2013 or 2015 and later onwards, right? We can see with a single compiler instruction, or with a single for example, I can say for each, right? In C++ or for .NET, or probably I think it's analogous to Java as well, right? Now these things would give me one single computational value. And that is nothing but if I want to add 10 different uh, uh, let's say each I have two arrays, each one of them is size 10, right? And then if I want to do an execution addition of array of A0 to B0, A1 to B1 as such, right? Now it's a one single instruction that would be fit enough for it to actually do it. But in principle, if it is much before 2013, before the advantage of C++11 or later standards, this would happen. This would happen. This would happen sequentially for each one of them, which essentially means nothing but 10 instructions, right? Saying that is the SIMD not available before? The architectures of SIMD, MIMD were always available. So essentially they were available before, but they were not so much available for usage, right? In terms of compiler support. Now, if you look for the same thing, for example, if somebody who is developing a gaming or using the CUDA language, or who were more specialized into developing of the OpenMP, using the OpenMP and building the applications, they were able to leverage it, right? And not in the traditional programming of available uh, programming languages and frameworks. But this eventually changed later on from 2012 onwards, and we can see many of the compilers and frameworks are able to leverage it. Uh, okay, the previous one, please. Previous slide, please. Okay, previous one, please. Okay, what we are seeing here, is nothing but when we say of pipeline executions. Now, essentially, what we have is nothing but uh, execution units, and then okay, what we have is nothing but a instruction set, and then which is being executed by the core or the CPU. And then of course this is associated with the memory or the cache, and then any kind of instruction set at that point of time would actually go for the execution unit. Now in traditional, what we could see is nothing but the down, actually we can see two multiple execution units, right? This is execution of two instructions per clock. For the same single clock, we are able to execute two instructions, right? Which essentially meant that two operations are being performed simultaneously at the same time instead of one single operation. So what it meant is nothing but, if I want to, let's say, if as a graphics, if I have a bunch of pixels, and then on the screen which I want to print them, let's say out of 1 million, I nearly have 5 million pixels that can be updated with the same color for Samsung, right? And then all of them can be parallelized for updation. And then this is a kind of operations that would actually happen in a just a blink of an eye, right? And then this is all courtesy of the SIMD, right? So that multiple data, one single instructions to execute on the multiple data sets. This would if you look at current CPUs and GPUs, these are SIMD is widely being used, right? Next slide, please. Okay, essentially, what is in a nutshell, all this is happening because of the extended register support that is that was available at the to do these operations. Right? Next step, please. Uh, yeah, these were actually introduced by the Intel and AMD in the x86 architecture. And then there is a support of 32 double precisions or 64 single precision floating point operations, and it's possible for 8 64-bit and 16 32-bit single operations to be done in parallel. Of course, all these things would have a deep implication to the domains and sectors that we discussed earlier, and then of course on the scientific simulations and artificial intelligence, deep learning, and audio video processing, and so on and so forth. Next slide. Yeah, okay. What we see here is nothing but a instructions and data, right? And then essentially what we are seeing is nothing but, on the top, what we can see is nothing but one instruction and one data set. And then this is resulting, let's say if I want to add two arrays, more or less what we discussed, that we are A plus 0 plus B0, which is resulting C0. We are actually doing three instructions, and each instruction supplemented with the data. So three executions. Now on to the right, what you can see is nothing but one single instruction and three data sets. And then this is resulting in one single instructions and three data executions at the same time. So instead of three iterations, we are seeing only one instruction causing the three executions, right? Which essentially meant that the efficiency is increased by threefold, right? So this is what the SIMD is meant for. Okay, next one, please. Now, uh, yeah, next one, please. Okay, now what we have seen SIND is on a single core and the ability to execute. Now we have multiple cores, and then each multiple cores. we have multiple cores, or the way the memory is supported in this is there is one set of specific memory associated with each of the core, and there is one common memory that would be associated with multiple cores together, right? Uh, and then there is one more amount of memory that would actually coordinate with the input output set of operations. Now, for us to actually do the parallelism, uh, okay, in the next slide, please. Yeah, perfect. Now, essentially, that's right. So essentially, what we can see is nothing but L1 cache, right? And then we have the L2 cache, and of course, uh, so any kind of operations or SIMD instructions that will happen on can be done for each one of the cores. And then in case if the multi-cores to be executed, it meant that each of the cores has to coordinate themselves. And then of course, the L2 cache would be used. The L2 cache would become a common cache, and then there is some synchronization mechanism that will come between the execution of core 1 and core 2. Apart from their SMD instruction set. Yes. Next one, please. Okay. Now, what we can see is nothing but dual core, dual socket motherboard in a node. And then next one, please. Uh, Next one, please. Now, I think now for a let's take a small example of saying that if I want to update some bunch of, let's say, 500 million pixels. Now, in a sequential way, if I want to keep on doing it without the GPU, it meant that the system would never be able to actually do it. Now, after the advent of GPUs, and then primarily for the graphics, supporting 1000 to 5000 cores, each of the cores would be able to execute on their own pace to do the SIMD operations, which essentially meant that the time has drastically reduced. And then when I take into combination of SIMD or MIMD for executing on the, which is in a way parallel executions across the clusters or distributed computing. Now, the amount of calculations that would take would be very, very minute. Of course, which essentially meant that I would be able to do the computations for the much larger tasks. Next slide, please. Now, each of the HPC system, unlike a traditional general systems which are available on the shelf, each one of them has its own set of signatures. And then each one of them, it's not like there is a one standard architecture that will be used across. Uh, each one of them, when it is built, is a combination of different hardwares, uh, a different set of hardwares, and then uh, each of the operating system, combination of the hardware and then operating systems, and the compilers available at that point of time. And then, of course, one thing that could be said of uses of the open source softwares, something like Apache set of softwares, or from the open source foundations. So they have always aided in terms of the future technologies, and then they are also being used. Uh, One of in couple of organizations, I could see that open source Red Stack, I mean, based systems have been built, uh, but they are for a small scales. Next slide, please. Uh, Well, ideally, it might so happen that each of the processes deployed would be scheduled, would be organized on the depend on the need of the application. But the ideal way is that all of them would be leveraged. Right? Practically, it would be much different. Of course, the efficiency of the system would pitch in at that point of time. Yep. Next slide, please. Uh, Yeah, I think there are different kinds of algorithms that would come into the picture as a part of the whether their execution is done in the parallel, or whether it is using a divide and conquer or pipeline or domain decomposition, so on and so forth. Essentially, all this is nothing but translating the main problem into small subset of problems and then executing them on the systems, right? And in one sense, all these things are more or less are the same kind of patterns that we can see being supported in each of the programming languages. Next one, please. I think these are very much widely known, so nothing much to delve into it. Next one, please. Next one, please. Yep, the previous one.
I have 5 minutes more.
Yep. Okay, so what distincts from a specific system is in terms of its ability to execute concurrently, right? And then ability to scale it up, right? And then of course decomposing the complexes into smaller components or the smaller set of problems as such, right? These are the desirable attributes, and of course there are some other factors that would also come into the picture. And then amount of computational capability it can support, amount of peak performance it can do, and then amount of power consumption minimized in a way, right? So all these things would come into the picture in deciding that. Okay, next one, please. Okay, okay, next slide, please. Okay, there have been good amount of standards that have gone in terms of building this parallel programming, right? Now, OpenMP and MPA is widely known. I have never seen this OpenSCC. CUDA is also being used widely, right? Now, in the yeah, though these are the specialized set of skills that you would not find way too many, but these are widely known, right? Next one, please. So, of course, parallelism is a fundamental technique of HPC. Scaling up of performance needs appropriate communication networks and software stacks, which essentially meant that it's not only computation but interchange of information between different computing components, which essentially meant that the networks have to support and they have to be timed appropriately. Increasing the number of CPUs was a traditional method, but it has its own set of limitations, and that's where we have seen that CPUs, DPUs, and different kinds of specialized chipsets have come into picture. And then we can see the number of cores of each of the CPU getting incrementally going on, right? And also the algorithms for combining these frameworks are also coming to the picture, right? Now, just next slide, please. Now, what we can see is nothing but as an observer, as an interest in the C++, right? C++ is one of the languages. It was so beautiful, and then it looked like it stagnated up to 2009 and so on and so forth. But interestingly, from 11 onwards, what we can see is nothing but tremendous set of standards ingested from different kinds of domains, and also from different different necessities of distributed computing. They're also getting ingested right now. It is in C++ 22 and 25, where we can see many of the specifications from the OpenMP are also taken in. They may not be in par with OpenMP. It's not like a complete alternative, but this is going in the direction of it. Next one, please. There is one more slide in between. Okay, now people who hasn't seen the CUDA or the OpenMP, you can just imagine it to be a bunch of compiler directives in the C++ code, whereby each one of them would give, in case of CUDA, we can specify which memory location to which memory location, which processor in a fine-grained way. Now, OpenMP is more or less in the same way we can envisage them. Yeah, I think this is almost end of my discussion presentation from my side. Yep.
Okay. Okay. Thank you very much. Thank you very much, Mr. Raghava. Excellent session on overall parallel computing architecture from the basics to as per your industrial expertise. Thank you very much. Audience, please ask any queries if you have. I think I didn't find out any query in the chat box regarding this parallel processing of HPC architecture or AI tools. Please directly ask the resource person, Mr. Raghava sir, for your queries.
I sincerely hope I haven't wasted your time. For me, most of this comes from whatever I have seen from the last 2 decades. It may not be much into your academic discussions, but this is very much based on the kind of industrial trends over a period of time. Yeah. If anybody has any quick questions, feel free.
I think the important slide is that sector feels current and evolving dynamics. I think everyone, hopefully you get this PPT, right? Maybe again go through that one. That's very interesting, and I see it's very informative also.
I'll just add a couple of points in this regard. Now, people has a understanding. People say that okay, as in more and more AI and neural networks and all these things comes into picture, it's possible that it have implications on the jobs and so on and so forth, right? It may be evident to whatever that is being traditionally being done, where there is a expertise that would be required professionally, but there is no creative aspect of it. But as we see, the problems are actually also getting more and more complex, right? And every time we reach to one problem, we'll have a new set of problems that will come into the picture, or we'll see much wider set of topics aggregating themselves towards into it and creating new set of problems, right? So in a sense that all this machine learning, data analytics, and then computing will aid us to create more and more set of problems and more set of jobs, right? It might so happen that in 1980s and 90s, accounting or having mathematics brilliantly could be very standards for getting a good job or doing something, right? But some of these qualities of what we think is very good might probably become centered around the technology, but it's very imminent that we are going to see new set of trends and new set of problems.
Okay. Thank you very much. On behalf of our ATAL FDP and our computer science department, Bonu Venkatachalame Institute of Technology and Science, and all my participants, thank you very much, Mr. Raghava, for your wonderful session. Now, I would like to introduce the second session resource person, respected Swarup sir from CDAC Pune. Is very expertise in high performance computing. Swarup sir?
Yeah, I'm there.
Very good evening, sir. Very good evening.
Good
sir.
evening. I think hope you are all able to see me.
Yes, sir. Yes, sir. Thank you, sir. Thank you, sir. Yes, sir. Yes, sir. Yeah. Your audio is good and video also.
I'll just share my this one.
Yes, sir. 1 minute, sir. Before your session starts, I request Mr. V. Anurag, co-coordinator of our ATAL FDP, to introduce our resource person, Sri Y. Swarup, sir. Y. Satya Swarup, sir, to the audience.
Good evening, sir.
Yeah, good evening.
I would like to introduce resource person, sir, Y. Satya Swarup, sir. Having over 30 years of experience in information technology industry, comprising of vast hardware, system software solutions, implementation of heterogeneous networks, with skill set of deploying, administrating, and managing of large-scale high-performance computing clusters. Key functionalities are providing consultancy to various agencies in setting up of secured environments, establishing of network, system and storage subsystems, setting up of data centers, drafting of IT policies for various organizations, and coming to major contributions, operations of Param 1000, 100 GF, HPC clusters, establishing and operating management of Param Yuva, 54 TF and Param Yuval, benchmarking the system for top 500 and green 500, preparation of various manuals towards operations, risk assessment, mitigation policies, documents, auditing of DC and DR policies. SAR is expertise in HPC cluster installation, configuration, and management of cyber security.
Yeah, I think thank you, Anurag.
Yes, sir. Thank you, sir.
Yeah.
Cyber security,
Yeah.
solution design and project guidance, fair knowledge of ISO, IT policies and guidelines, and file systems include UFS, NFS, EXT2, T3, NTFS, FAT32. Coming to awards and certifications, Executive Director Commendation Award for the year 2022, Certified Cyber Security Professional, Certified Operator Extreme Back Diamond Switch, Unix Administrator, Hardware Servicing and Maintenance SCSI. These are the various awards and certifications the SAR has achieved. And SAR has an experience as a program director for HPC AI in infra and operational levels 13A in CDAC Pune, Center for Development of Advanced Computing, from Jan 12th to 30th September 2024. Experience in setting up of operations and e-sign, experience in drafting of various IT policies. These are all some of the benchmarks of SAR achievements. So with this, I conclude the introduction of our resource person, Satya Swarup sir, Eramilli. Thank you, sir. Thank you very much.
Yeah, thank you,
Yes, sir.
Anurag. So
Thank you, sir. Thank you, sir. Please
give me a minute. I'll
end
share
our
my
session.
screen.
Thank you. Thank you. Sir, share, sir. Share your screen, sir.
I think I have been given access to share it.
Yes, sir. Sir, so co-host rights has given, sir.
Given? Okay.
Yes, sir. Yes, sir. Already given. Sir.
Okay. Let me see. So are you able to see my screen now?
No, sir. I have shared, sir.
Yeah, I've shared it.
Okay, sir. Yes, sir. Yes, sir.
right?
Yes, sir. Yes, sir.
Is it in full screen or no?
No, sir. No full. It is not full screen. Just keep in full
Now
screen.
it is in full screen?
Yes, sir. Yes, sir. Yes, sir.
Yeah. So good evening, all of you.
Yes, sir.
And today I'm talking about like this HPC architectures, what we talked about yesterday, today. So many of us are already talking about, many of the architectures, and there's no difference what I'm going to talk, but I'm going to stress it upon some of the what you call the building blocks of the HPC, and then really how a system administrator point of view, like say how a user point of view, the jobs will be running on the system. Okay, like say the process scheduling, which is I'm going to cover it. But before that, I'm going to cover some of the aspects with respect to the terminologies and what we are talking about today's technologies. Okay, so people talk about a lot of things, but I want to stress upon a little bit extra mile on, because I'm the hardware person, so I have to stress it upon that what is that hardware we are talking about. Okay, so this is my outline. The outline of the presentation is that the approaches of various architectures, what we are talking about, and of course, in today's scenarios, even if you take any of the supercomputer, it is a mixture of hybrid. We call it as a hybrid supercomputer. So whenever you call it as a hybrid, it is a CPU plus a GPU. Okay, so you call it a GPU, you call it as a accelerator, you call it as a coprocessor, it is all same. So it is like a hybrid in nature. And then what are the building blocks? Like say, what are the key building blocks of this HPC, any of this HPC system? We are going to touch upon that. And then followed by the process scheduling and what are the resources, what are the methods of scheduling and the accounting. Okay. So we call it, like say we talked about in the yesterday also, today also, we talked about large SMP systems, that is multiprocessing systems. So now NUMA is one architecture, CC NUMA is another one. This is a cache coherent NUMA and the cow. I think people are talking about a today's supercomputers. Now we call it as a cow, that is a cluster of workstations. The workstation or a server, it is all same. Depends on the resource. We call it as, like say when you have a visualization and other things, we used to call it as a workstation, but more or less the resources are same. So the cow is a universally accepted architecture to build supercomputer, that is cluster of workstations. Like say if you take any of the supercomputer today, it is a cluster of multiple systems. Okay. So now we come to this see this architecture of this NUMA architecture, that is a non-uniform memory access. So if you see that, I think you can see the cursor. If I move my cursor, right? Now you see the CPU 0, CPU, you have the 4 CPUs in a node, okay, which are connected using a high performance interconnect, that is a QPI, quick path interconnect in case of, the Intel. Now the Intel has moved on to the next interface also. So whenever I talk about interconnects, there are two types of interconnects. One is the CPU interconnect. So the CPU interconnect is different from the interconnect which is connecting the nodes. Okay. So there is a difference between these two. Okay, we'll come across in the subsequent slides what is the difference. So if you see this architecture in this, like say this is a 4-way SMP, we call it as 4-way because it is a 4 socket. Okay, and then multiple cores on each of the socket. Like say the cores may vary from like say, up to 64 or a 128 core, whatever it is. And now the memory is there. So the memory, what you are seeing is the memory is local to each of this particular core. Okay, we'll see in the next slide the difference when you talk about a NUMA. And then you have typically you have a cache, and then you have the memory, and you have a PCI Express bus which is connected for connecting all the peripheral interfaces. Like say when you talk about a GPU, when you talk about any of the additional interconnect interfaces like InfiniBand. So everything is going to sit in the PCI Express bus. Okay, this is the IO. We call it as IO bus, and this is the memory, and this is the cache and other controllers. Memory controllers are built in within the die. Okay. Now let us go to the next slide. Now, if you see this, you'll get much more clarity here. Okay. The clarity in the sense is, what is this? You can see in the slide. There is, like, say you have the multiple CPUs. You take like a socket, and the socket is having again multiple cores. Now you see that each of the core having its own L1 cache, and you have a L2 cache. Okay, whereas L3 cache is shared. Okay, so the L1 cache is the fastest cache what we are having, that is the data and the instruction cache, and then followed by the L2 cache. And these caches are very less in the capacity but very high performance. Okay, means the IO is very fast, the latencies are very less, and I can discuss in the subsequent slides. So this is how it is. The shared cache is only the L3 cache. Okay, so the up to the L3 now it is all in the same single socket die. Okay, now when you go to this, for example, if you see that whatever is written in this text, you can see that some AVX is there, which is a Intel proprietary kind of solutions, that is advanced vector extensions, and FME is a fusion matrix and addition. So these are some of the instructions which are associated with the Intel CPUs. So LUMI is I have taken the slide from that. Okay, the LUMI stands for the large, unified modern infrastructure. So why this LUMI is formed is to, it's a European outcome. European countries, they have come together to form the exascale supercomputer. So that is how the LUMI has come from. Now let us go to the next one, CC NUMA. So everybody talked about NUMA and the CC NUMA. The difference between these two is very, very, you have to be very careful in observing that. So the cache coherency, when I talk about a cache coherency, means, for example, a particular, the cache is written at a particular processor, that same should be reflected on the other one. So what is needed here? You need a high throughput, low latency kind of network, which is connecting all the sockets and the memory bus. Like say the memory bus is connecting all the sockets memory, and which is ensuring that the cache is replicated at all the places. Now this kind of systems earlier, which is famous, okay, before this cluster workstations are formed. Why they are famous? Because they used to offer more number of processors, like say 512 sockets and 1024 socket kind of missions, which are tightly coupled and integrated within a single system. Okay, and why it is failed? It is not because it is giving high performance, but it is not failed. I'll say that it is outdated because of the expandability what the new systems are giving, the scalability what the new systems are giving. Okay, otherwise the performance wise they are very good, but the scalability wise it is very difficult. And as the sockets are increasing, then your memory bus length is increasing, and then you are finding a single point of failure and other things. Okay, so come back to the next. Now this is the future what we want. Okay, what we want, like say if you see today, when we talk about a CPU, and everybody knows that, okay, in a system, I can get a 1 TB of memory to 4 TB kind of memories. Okay. Like say I have a chips available, 1024 GB kind of chips are available. Now, the question is that when it comes to the GPU, like say you have a NVIDIA GPU, if you take a H200 or something, which is having 18,000 cores, and then 18,000 cores are fighting for a 144 GB kind of memory. Okay, so because the architecture is different, the usage is different, the placement of that particular hardware is different for a particular solving a particular type of problems, it has been evolved. But at the same time, the programming paradigm, if you see that, it is very difficult for the users because of they have to handle the memory very carefully. It's a very costly resource to utilize a memory on the GPU, because you are having 18,000 cores fighting for a very small memory. Whereas if you take a CPU, a 64 core having a 1 TB of memory. So there is a huge difference between this. So what we want is in the future, we want a GPU, CPU accessing the same memory. You able to utilize the entire memory, whatever is the system memory is there. So that is what we want. Okay, that is the future. Like say if you see here, the CPUs are again, CPU, GPUs are connected with a, high-speed interconnect. And similarly, CPUs are also now the CPUs are connected with high-speed interconnects, whereas the GPUs today, they are all still rely on, the PCI Express bus, right? Now the PCI Express bus is 10 times slower than the CPU bus. Okay, we'll see in the subsequent slides why it is so slow, or what are the figures. Okay. And I think you can stop me wherever you are having any doubts. Okay, I think audience can ask questions. Now this is the typical. If you see the any of the architecture of a, what are the building blocks? If you see that a cluster. Now you can see this. These are all the small nodes. If you take this as a rack. Okay, now you have a number of racks, and then these are all small. Each of this is a, a workstation or a server. You call it as a server, so it is a server. Now all these servers are connected using a high-speed interconnect. So this is a interconnect which is connecting the nodes across the cluster. Okay. So this high-speed interconnect is maybe a, slingshot, or it can be a from an what you can know, the IBM's interconnect, or it can be a TOFU interconnect, or it can be InfiniBand interconnect, or it can be a permnet. Okay, so these are the interconnects. The nature of the interconnect is that it should offer a high speed, high bandwidth, and low latency. That is the requirement of an interconnect. So when you see the other side of it, the other side, it is connected with a normal Ethernet management network. Okay. So the Ethernet is used for the management of the nodes, like say the OS deployments, or, providing the access to the system, or a monitoring of a system. All that can be achieved using this normal Ethernet network, because the Ethernet network today, it is also scaling, like say you are getting a 400 Gbps or a, 100 Gbps kind of networks are available. There are clusters in the top 500 which are with the Ethernet also. Okay, but if you see the latency of it, still the proprietary interconnects are having low latency. So you see that these are the nodes, and then I have some login or access nodes, and some visualization nodes, and some monitoring and management nodes, because the system need to be managed and monitored by somebody, all the services. And then you have the file systems underlying. The underlying file systems are like, say you have a file store, and which is like a parallel file system. And usually the parallel file system is having a metadata associated with that. Okay, what is that parallel file system? How it is different from a normal file system? Like say the data what is to be written is, made into the data chunks, multiple data chunks, and these chunks are written across the, storage blocks. Like say across the multiple storages, you can say, you just imagine that, like say there is a 10 server storage. Okay, storage nodes. Now the data is written across these 10 systems or 10 blocks. Okay. Now that is a parallel file system where, because it is offering a high throughput, because I am able to read parallelly from the multiple storage nodes, I am able to write parallelly to the multiple storage nodes. Okay. But what is written where is maintained by at the metadata. And always the metadata is required to be at a HA kind of setup, because you cannot lose the entire data, because if metadata is gone, you cannot recover it. So that is the HA is required for the metadata. And then the industry today is coming on to the object storage. The requirements are coming to the, like say, image processing, large image, the solutions requirement is a large image chunking, processing, matching. So a lot of things are happening on that front also. So you need an object storage. So these are kind of, the major building blocks if you see how the system looks like. Okay. Now you come to the GPU. So I spoke about, that you have that, I said there is a compute, that is a CPU, and these CPUs are connected with a high-speed bus. Now, if you see that Intel, now you are talking about there are two types of processors. One is a sys and another is the RISC processor. One is a complex instruction set computing and another one is a reduced instruction set computing. So both are faring equally good, and they are having their own advantages and disadvantages. Now, if you see the bus speeds, now you'll understand what is the speeds I'm talking.
We'll see it.
Yeah, hello?
Right.
Hello?
Huh?
Yeah. So if you see the bus speeds, now I'm talking about which is a connecting the CPUs. Now the connecting CPUs is a QPA stands for quick path interconnect, whereas UPA stands for the ultra path interconnect, which is the latest interconnect from the Intel, which is offering around 141.6 GB per second. Now there is a difference between a capital B and a small b. I think you are aware of it. Like say, whenever I talk about a network speeds, I talk about a small b. Whenever I talk about, this is a bus speeds or a storage, this kind of speeds, I talk about a capital GB. Okay. So this is a CPU bus I am talking about. Now, if you take this, you please read it as AMD. So the AMD, if you see that, EPYC processors, that is a 128 core processors. Now you talk about, there is a Infinity Fabric, the hyper transport, they call it as earlier hyper transport. Now they are calling it as Infinity Fabrics, which is offering around 72 GB per second. Okay. Now you come to the RISC processors. Now Sun Micro is having the Spark 64C. Now the Spark 64 is not having a relevance because you are not getting the Spark processors. But still in the top 500, there is a Fujitsu supercomputer in Japan, which is actually developing this, the Spark, Ultra Spark system. They are still using that processors. And then they are having a Fireplane interconnect, which is also latest interconnect, which is offering a 43 GB per second. Now, if you come to the IBM is having power processors, which is of 96 core, and then they have come with a CAPA, that is CAPI, that is a processor bus, that is a copper accelerated processor interconnect. Okay, so they are using a copper lanes to connect these processors, which is accelerated bus, which is giving around like say 375 to 409 GB per second. So we are still talking about a processor interconnects. Okay. Now you come to the ARM processor. If you take it ARM, they're having like say you have the 192 cores, and then like say AMBA is their bus. That is a, that this is an advanced microprocessor bus architecture. Okay. Now this is offering a 30 GB per second. Now let us not fix up and decide that, okay, this is faster or this is slower, because the latencies also matters, and the way the number of processors being connected also matters. How the cache is handled and a lot of other instructions are handled. Okay. But I am talking about just to what you can know for the awareness, we are talking about what is that bus connecting, which is connecting the CPUs. Now, if you take a Sunway, that is a, the interconnect, which is of, Sunway interconnect, that is a 51.2 Gbps. And then NVIDIA, if you take a Grace Hopper, that is a super chip, which is a recently, launched the chip, which is offering a NVLink, which is offering an 100 GB per second. So these are the typical bus speeds where we are talking about when you are connecting a CPUs, because the CPUs need a high throughput communication between among the CPUs. Now you come to the GPUs. Like say now we touched on the CPUs. Now we'll come back to the GPU. In the GPU, we have the NVIDIA, AMD, Intel. These are the major players. There are some other players also there. Okay. And CDAC is also having something called RCS, but that doesn't come under GPU. That comes under a, accelerator. Okay. So what is that these are offering is like, say, if you take a H200, that is 18,432 CUDA cores and 528 tensor cores. Okay. So these are the kind of cores which are there. Like say these cores are for the some are this This 528 are like say you talk about instruction sets, and the remaining are very good in the stream processing and other things. Okay, major processing cores. Now, if you come to the AMD is having that MI300X, that is a 19,456 stream processor, 304 compute processors. Okay, so Intel Intel has come with a Gaudi 3, that is a 64 tensor cores and 8 compute cores. So here again, see, the Intel is actually, we can say that, okay, Intel is actually way below compared to the other two, in compared to the number of cores what it is offering. But what you can know, remember that each of this, the processor technology or a GPU technology is actually associated with a particular, the problem, addressing a problem. Okay, like say for example, I want to address a particular problem which needs a, some vector instructions which are actually available in Intel Gaudi 3, I'll go for it. Like say, if I want a benchmarking, I want a highly ranked benchmarking, I'll go for the AMD. I want some, libraries are available, which are, I'm able to see some visualization. I want to do some AI kind of computing, I'll go for NVIDIA. So it depends on the use case. You can select what is that, GPU which suits your requirement. Okay. So to compare the GPU versus, like say CPU versus GPU, so the CPUs are having higher floating operations, that is a 32 flops versus a 2 flop. Okay. And similarly, the memory, you see that as I mentioned earlier, the memory available for each core is a 32 GB, whereas for each GPU core, it is only 0.0074 GB. So there is a huge difference between still that, how we are going to use the GPU and the CPU. Okay. So whereas, like I mentioned, so the matrix calculation, the tensor and compute are good, and whereas CUDA and stream processor general purpose. Okay. So now come to the memory, next slower part of the system. Now you say the fastest of it. Now we'll come to the next slower one. That is, we are talking about a cache memories. Now, when you go to the cache memory, you have three types of cache memories. We talked about that, L1, L2, and L3. Okay. The L1 cache, these are all static RAMs, and which are around 0.5 to 100 nanoseconds. Like say L1 is working at a 0.5 nanosecond, and L2 is working at a 10 nanosecond, and whereas L3 is working at 100 nanoseconds. So you see the difference between this. Like say how costly it is when. So everybody can think about it, like say somebody says that why L1 is not having, more memory. So there are a lot of, restrictions. It's not only the cost, it is also the placement and the space available on the die and the power, consumption. Okay, there are a lot of limitations when it comes to that number of transistors which are sitting into that, the die. So when you go to the GPU, you have a GPU, the GDDR6 is very good. That is a graphical DDR memory chip, which is offering a 21 Gbps and 0.9 nanoseconds, 0.8 nanoseconds kind of, the latencies. So if you go to the server memory, the next slowest one, okay, that is a server memory is DDR5, which is, 6400 mega, this one mega transports per second, that is working at a 16.67 nanoseconds. Now you see that, like say you are talking about 5 nanoseconds, and you are talking about a 10 nanoseconds, and you are talking about a 16.67 nanoseconds. Now, when it comes to the secondary memory, I have written that only a secondary memory. Actually, we are not. Today, people are thinking about, the using, like say, my memory is less. So what I'll do is I'll use a NVMe kind of, SSDs, which are not very fast like memory, but they're comparatively good, and the chips are available. Like say, I can have number of these SSD chips, which are giving around 20 microseconds. Okay. So when I talk about nanosecond, that is 10 power 9 minus 9, and when I'm talking about a microsecond, that is a 10 power minus 6. Okay. So SSD and M2 bus. M2 is a, that next generation bus, which is also, which is also a key form factor in many of the systems which is coming, which is offering around 25 to 100, microseconds. So these are all mapped as a memory in some places. Otherwise, for a faster I/O, you can use it as a storage. So come to the storage architecture. Like say in the storages, you know about what is a NAS, what is a SAN. You know that the NAS is a network attached storage, and the SAN is a storage area network. Okay. So the typically NAS is offered over top of the Ethernet, where the protocols offered are AICTE, that is for the block, and NFS or a CFS, that is for accessing the network file system or a shared file system over the network. Okay. When it comes to the block, I have to use AICTE. So typical VMware deployments, typical any of the virtualization environment, they'll be using mostly the AICTE. Okay. In worst cases, they can also use the NFS. Okay. And come back to the next, the storage area network. The storage area network is like, say, you have a FC, that is a fiber channel. And of course, you can also having interconnects, which is InfiniBand or any other interconnect, which is connecting to the storage area network. And also the Ethernet. Okay, these are the three standards which are being used as the storage area network when it comes to the supercomputers. But still again, Ethernet is having its own reservations, like say the latencies and other things. Okay. Now, when it comes to the file systems, the most widely used file systems are Lustre. That is a parallel file system, and the GPFS is from the IBM. Okay. And then the PANFS is from Panasys. Okay. And NFS and PNFS are also widely used. The difference is the NFS is actually a serial protocol. So it looks like a parallel, but the protocols is a serial protocol. So the write is written on one by one, and whereas you don't see that because that is a very faster write. And PNF is a parallel NFS where you are using some of the parallel threads to write to the IO storage. Okay. Now come back to the interconnect. We talked about this interconnect which is connecting all the nodes. Okay, it is not the interconnect which is connecting the CPUs, which is connecting the nodes. Okay. Now you have the permnet. So the permnet today CDAC developed in-house permnet, that is a 6D torus. That means it's a multi-dimensional network. Like say from any node I can connect to the other node with 6 different ways. Okay, that means 6 different lanes. Now each of this lane is offering like say around like say 600 Gbps. One direction I'm able to give 600 Gbps. So I'm able to for 6 directions 6 into 600 Gbps. So that is what the torus architecture, but it's very difficult to scale. It's a very complex to scale. Now imagine that you have a like say 128 nodes which need to be connected with a 6D torus. So you need to really calculate how many connections and then how it has to be laid down. Okay, it's very difficult to go for a non-blocking architecture. So what is the non-blocking? Non-blocking means from any node to any node, I am able to pump the data at the same speed. Whereas a blocking architecture means I am using multiple level of switches in between. Okay, so that I am able to connect n number of nodes. There is no limit on number of nodes what I am connecting, but it's a blocking architecture because I am connecting at a multiple switches, so I am increasing the hops. Okay, when I am connecting more than one switch, then there is a hop added. So whereas in the torus network, there is no switch here, it's a switchless architecture. Okay, so that is always gives a better performance. Now InfiniBand is the next one, which is widely used across all supercomputers, which is a 200 Gbps and then 90 nanoseconds. And see the latencies are very, very low. And the NVLink, that is a GPU to GPU communication, which is a 1.0 TB per second transfer rate with 20 to 50 nanoseconds kinds of latencies what it offers. And GPU Direct is a technology by NVIDIA, which is actually accessing a remote memory. So RDMA stands for remote data memory access. So which is around 10 GB to 25 GB kind of, I'm able to give the throughput over the GPU direct. So the slingshot is another interconnect from the crane, ARIS network and the slingshot, which is 200 Gbps at 8.7 microseconds. And TOFU is from the Fujitsu. I talked about the Fujitsu, which is a top 100, which is there from Japan. And this is offering a 45.82 GB per second with a 0.49 microseconds. Sunway from the China, which is a 1 microsecond latency with a 16 GB per second bandwidth. And OmniPath is an Intel interconnect, which is 100 Gbps and which is a 0.9 microseconds. So these are the various interconnects which are available in the market today. And each and every day, there are up and downs, and somebody is coming with something new. And this fight is keep on going, and we'll see that in future many of them may merge, buybacks and then merging the technologies, and things are happening like that. So come back to this system softwares. Like say we have seen the building blocks. Like say you have the CPUs, you have the GPUs, you have the parallel file systems, you have the interconnect, you have the management network. You have the login nodes, you have the access nodes, you have a visualization nodes. Now, what is that contains all these nodes? These nodes are contains these softwares, like say parallel programming softwares, which are from the, we call it as a system software, which is provided by the, the respective, OEMs. We call it as original equipment manufacturers, or you name it as Intel or AMD, whatever it is, or NVIDIA. Okay. So that MPI, OpenMP, pthread, C, Fortran, Python, Coda, etc. These are various programming, languages are available. And the compilers and the libraries are very important. Like say when you write a program, you have to compile it, you have to parallelize it. And Pascal is one good compiler. And then Intel and AMD, Pascal, NAG libraries are there. And then MATLAB and BLAST. These are some of the libraries and the compilers. Okay. And these compilers are used to compile a particular program and parallelize it, and then, ready to run it on the system. Now, when it comes to the schedulers are PBS Pro, Mob. Okay, then your Mob is a open source of the PBS Pro and the Slum, and then you have the LSF, Grid Engine, Hadoop. These are some of the schedulers where I can schedule my job. And accounting is again, you have the Gold, Slum, and some other software, external softwares, or you can integrate with this schedulers. And the application softwares, we call it as like say any software which is used for solving a problem for major application software. Like say ANSYS or OpenFOAM or a PAM Crash, Quantum Espresso, BioRuby, weather research and forecasting. WRF is weather research and forecasting. So these are some of the. So these software are important. Its hardware cannot do anything on its own because you need the entire stack. So can I go ahead and it's fine?
Yes, sir. Yes, sir. Please, sir. Please, sir.
Yeah. So coming to the schedulers. Okay. Now, what is that you need in the scheduler? What you need is a JavaScript. Like say there is a script, there is a format in which I need to write so that the scheduler can understand, right? Like say, for example, I want the CPU 4 numbers. Okay, I need GPU 1 number. I need what you call memory this much, and I need a storage this much. So all these are all resources, right? Storage is a resource for me, memory is a resource for me, CPU is a resource for me, and the GPU is a resource for me. And most important thing is time is a resource for me. Time. What is the time my particular job is going to run? Is it going to run for 1 day? Is it going to run for 7 days? Is it going to run for 1 month? What is that I am asking about? Okay, so the resource is also important. Time is an important resource apart from GPU, CPU, memory, and the storage. The job submission. The job submission is like say a particular command to submit your job after you have written the entire description in your job, where your output file will be written, from where I have to take the input file. All this comes onto the job script. Okay, the job submission is only a command to allow me to submit the job. Next comes the resource manager. So the resource manager is the one which is actually managing all the resources, which knows that what is the resource, like say it is reporting to the, the other stack, what is the resource availability, okay, where the resource